All right, the goal in this video is to talk about the uncertainty principle. Sometimes it's given the name Heisenberg uncertainty principle. And let me just talk about that briefly. Let me get this up on the board. Look, there's a lot of amazing videos out there with amazing graphics that are way better than what I'm going to do in terms of graphics. So you should watch those. I'll put some links in the comments. But I wanted to kind of give you a feel for also how to pass a test with a Heisenberg uncertainty principle question. So if you want, we're looking at page 75, workbook volume 5, and let's just go through some terms. Here is the uncertainty principle. Delta x, delta p sub x greater than or equal h bar over 2. You call this symbol h bar. Now, what do all these symbols mean? Delta x would be called the uncertainty in something's position, or an uncertainty in a position measurement. So measurement is a key element here. Delta p sub x, this is the momentum in the x direction component. So it's the uncertainty in momentum in the x direction measurement. All right. H bar is Planck's constant over 2 pi. It ends up being this number. Notice it's a very tiny number. Well, we're talking about uncertainty in measurements. Let's look at some measurements. Imagine I take a ball, maybe, I don't know exactly the mass of a baseball, but this is probably in the ballpark there. So, and 20 meters per second might be, about 45 miles an hour or something. So this is, let's just pretend this is a ball, kind of like a baseball, I don't know the exact mass, being thrown at about 45 miles an hour. Right? There are uncertainties in the measurement. So there's some uncertainty in the mass of the ball when you put it on a scale. There's some uncertainty in the speed of this when you use a radar gun or maybe you use video capture. There's some slop. So there's some uncertainty in these measurements. Well, that means the momentum here is 3, but what's the uncertainty in that measurement? Doing our lab techniques, error analysis. If we assume the mass measurement is independent from the velocity measurement and the errors don't combine, this is the fractional error in mass, right? Notice there's no units, kilograms over kilograms. So just to be clear here, in case you've forgotten your error analysis, this term right here is delta mass. It's 0.001 kilograms. So basically you're off, it's 150 grams plus or minus a gram, right? And here, let's make this 0.1. Sorry about that. All right, and so this term right here would be delta V, the uncertainty in measuring the speed. Well, we could propagate that through using our propagation of error formulas, and let's say we end up getting this. I found about 0.03 or 0.025 kilogram meter per second is the error in P. All right, so the uncertainty in measuring P is about this number with these, this number with these units. We usually round errors to 1 sig fig. I kept an extra digit when I plugged it in here in case you're wondering. And then the final uncertainty here, I'm going to round to 1 sig fig. So the uncertainty in the position of the ball is 2 times 10 to the minus 33 meters. Let's think about that number for a second. An atom is about 10 to the minus 10th meters in size. A nucleus of an atom might be about 10 to the minus 15th meters in size. So we're looking at something that is, I don't know, 15 orders of magnitude smaller than the size of a nucleus, or even smaller, right? So yeah, almost a billion times smaller, a billion, not a billion, a billion times smaller than the size of a nucleus. What is this saying? What this says is the uncertainty principle is a pretty stupid principle to apply to real life objects like cows, frogs, tacos, people, balls. But in this case, it might be important if we get to a small enough scale. And so now I want to do a screen share with you. So for things like electrons and photons, this starts to matter. And again, watch the video. I'm just showing you the pure math with a simple example. Let me go to a screen share right here. All right. I'm going to start by talking about a wave packet. All right. So in chapter 15, we talked about Fourier analysis, right? Where basically if you add up enough cosine waves or sine waves, with this ends up being, right, when we add all these up together, we get this repeating pattern here. All right, this pattern, and notice it goes on for forever. Let me clear all that out. We're adding those up, right, and we get this interesting repeating pattern. Now I want to show you what happens as we add more and more waves, and to do that, I'm going to make some adjustments here, and I'll link this in the notes afterwards. As I add more waves, notice what happens. As I add more waves, we see a larger gap between this part of the signal and the next one, right? So basically, as I add more waves, you could think of that as like adding more momentum, I more precisely locate the particle. Okay, maybe that helps you, maybe it doesn't, but let's just keep going. I'm going to go to an absurd limit here in just a second. We're going to add even more waves, right? And then, right, if you go to an infinite number of waves, you get a single packet that's just sitting there in space. You could think about this packet, right? It's a particle, it's a wave, it's both. This distance you can think of as some kind of uncertainty, sigma subscript x, or you could view that as delta x, right? These are the two terms that you'll sometimes use. So you'll notice this computer program is talking about sigma x. And so it looks like the uncertainty in this packet is about a quarter. So to be clear, that's like the, right, that relates to the standard deviation of this bell curve, right? So that's what this is talking about. But that's essentially, it relates to the width. It's not exactly the entire width, it relates to the entire width, all right? Well, I guess you could say this goes on to forever and goes to zero for a long ways. All right, point being, we have this packet, right? And so this packet could also be moving or traveling. And I've got another sim that's going to show that. And so the traveling, right, it has some momentum associated with it and some uncertainty associated with that. And we will go through this and calculate some things in a later chapter when we get to quantum mechanics. But just for now, basically, I want you, not p sub x, delta p sub x. So p sub x is the particle's momentum, sigma x or delta p sub x is the uncertainty in that. Okay, again, watch other videos. This one is not the be all end all, but let me show you one more bit here. Let me move this so I can see, what was it? I want to go to this one. All right, this simulation is paused right now. Maybe I'll play it for a minute. This is an example of that uncertainty relationship, and we'll go back here and talk about this. I want you to imagine that this is a wave packet that we were just describing, and it has some momentum. It's moving to the right, okay? So there's some speed, or you could think of it as having some momentum, traveling to the right. So it has some p sub x. All right. Now, there's an uncertainty. There's basically some width of this packet, which we would call delta x. There's a width associated with this packet. That means there's some uncertainty in the momentum. Because there's some uncertainty in the position, and notice, look at the size scale now. We're talking about things that are nanometers in size. So, right, very small objects. The uncertainty now becomes non-zero. As a result, what first is a very localized packet will get spread out because there's a lot of uncertainty. If we try to measure the packet's size, right, there's uncertainty in its size, which leads to uncertainty in its momentum, which leads to the packet spreading out. Let's watch this again now that you've heard that. And whoops. Here we go, 3, 2, 1. Notice the packet gets wider and wider. There's more and more uncertainty in the position over time, right? The packet gets very wide, and so that's great. Now I'm going to run this one more time and talk about what happens when we make a quantum measurement. We're going to collapse, and we haven't talked about quantum mechanics yet, so if you want to stop the video and wait for later, that's fine. But I'm going to rerun this. Let's step this back, right, and make this a little bigger. Make this a little bigger. All right, so I'm going to run this, and when I make a quantum measurement, what that's going to do is it's going to suddenly restrict the location. I'm going to measure where the particle is located very precisely. And when I do that, I get a very small value of delta x. And let's look at this equation really quick. Let's get this equation on screen. Delta x, delta p sub x is greater than or equal to a tiny number, h bar over 2. Solving this for the uncertainty in the momentum, that's got to be greater than or equal to h bar over 2 uncertainty in the position. What's going to happen is when I hit this button here, make a quantum measurement, delta x is going to become very small. We're going to localize the particle to a very small region by measuring it, maybe with some photons or whatever, right? So when this number here drops to a tiny value, this number should skyrocket, which means making the measurement causes the momentum to go crazy because the uncertainty or the error in the momentum goes crazy. In practice, this means measuring the location of an electron means you know where it was when you measured it, but suddenly it's flying all over the place and you don't know where it's gone. So let's watch this play out. Here we go. I'm going to make a quantum measurement in just a minute. And notice it starts spreading out faster. Over time, it's still propagating to the right, but you might have noticed as we replay this, look, did you, oh man, let me see if I can get this again. Okay, let's play this. Oh, sometimes you'll see it jerk to the left like that, and that's kind of cool. And as this spreads out over time, oh, now it's gone. All right. We'll go over this more in class, but I just thought maybe this is a good introduction. I'll put a bunch of video links in there, and if you really want to understand this, you might watch those videos instead of my simple case. But this shows you how to basically pass an exam question, which is not bad either.